In this video, I wanted to show how I did a Centroid retrofit for this Lagun Matic 250 CNC mill that has a Dynapath computer and interface. This machine has seen a lot of use and will definitely need more work done to it after the retrofit. But the client, which is a friend of mine, simply was concerned with controlling the mill with a more modern and intuitive interface, so I recommended Centroid. Before I start with the retrofit, it's worth mentioning that I have personally programmed and used this mill for at least 2 years. I've made various parts on this mill from different materials. Some of these parts had fairly tight tolerances that the machine could hold very well. It was the first real CNC mill that I learned to make parts on. One time I even set up a tapping operation with a tapping head in the spindle. This was nerve-wracking because the spindle does not have an encoder, nor did I have a tachometer to measure any speeds, so I had to set the spindle speed manually. Another time, I tried thread milling, which was really interesting as well. I found it hilarious that I successfully made metric threads with an imperial tool. I want to show you a little bit more of the machine before I start taking things apart, like this nifty floppy drive on the back of the machine that I never used. This Dynapath controller had a COM port on the side of it, and to truly use this machine to its fullest potential, I had to send G-code through this port. To do that, I had to get a specific cable called a null modem or crossover cable. This was simply wired in such a way to allow two devices to communicate properly. Then you just set up the COM ports, which is really simple. All you have to do is read this entire manual, and after pulling out all your hair, you go into the Program Catalog menu and type in the secret cheat code, RS232C, and enter that to activate the buffered input. Of course, everybody knows this. You'll know you did it right when you go back into the Transmit/Receive menu and you get this text. Setting up things on the computer side is much easier, and I loved using this program called DNC4U. It was specifically designed to interface with old controllers like this Dynapath, so it makes it a lot easier to transfer G-code over via drip feed, for instance. For really simple operations, I got pretty good at writing G-code programs manually. Once you understand how the machine moves with certain G-codes and parameters, you can be as creative as you want with your program. For more complex geometry, I simply modeled it in Fusion 360, and luckily there was a post-processor available for this controller that made the proper toolpaths. As you can see, when you first turn on the controller, it throws a bunch of faults at you, and you have to manually clear them and reference, or in other words, home the machine before it will allow you to use it. This is of course all normal, but I want to just show this so you can compare what happens at startup on the Centroid controller. I took a quick look under the bed of the machine to just inspect the ball screw. I was curious what the diameter of the ball screws were for the X and Y axis. They turned out to be 1¼ inch in diameter. The Z-axis had a 1-inch ball screw. Something that's pretty interesting is you will notice that the knee of the mill can also move the Z-axis of the machine, but there is no motor here. That's because the weight of the entire knee could stress out the motor. Even turning this handle by hand can get tiresome. So that's why you typically see the quill of the machine motorized, because there's far less weight there to move. Up on the top end of the machine, you'll see one of the servo motors, which we'll talk about in a little bit. Above that, connected to the spindle, is the air-powered drawbar system. I believe this is a power lock system, but I'm not entirely sure. A powered drawbar makes it so easy to change tools on this machine. I can't imagine changing every tool manually. And the tallest thing we have on the machine is the main spindle motor, which is a 3-phase, 5 to 7 horsepower monster with a built-in braking system to slow down the spindle faster. On the other side, you'll notice the lever where we can change between our low and high gears, and then the hand wheel that's there to change the RPM only while the spindle is running. Again, the controller can't adjust the RPM at all, and the new Centroid one won't be able to as well, only because we would need a behemoth of a variable frequency drive in order to allow the controller to do that. And last but not least, behind the machine you'll see some solenoids used for the air-powered drawbar system, and some reservoirs that are filled with oil, which are for the one-shot lube system that lubricates the spindle and ways of the machine. Just below that, you'll have the entrance to the flood cooling pump, and the only thing I'll say here is you'll have to plug your nose and hold your breath as you poke your head in there, or you might pass out. This is also not my mess. This coolant pump was never used since the machine was bought. We attached a separate mist cooler system to this machine, and that was always maintained. Okay, I know you're probably itching for me to get started, so what I wanted to do first was complete the mechanical assembly and then do electrical last. I opened up the cabinet, and there's a lot of things going on here, but I'll simplify this a little bit. Once you turn on power, the transformer up here is energized and turns 240 volts AC to 120, which powers the computer first and allows it to boot up. Then when the computer is ready, you will need to press the machine on button that triggers the two first relays here. That allows power to travel to the rest of the components, such as the servo drives, which are sitting here. The rest of the relays are for triggering the contactors up here that control the forward and reverse rotation of the spindle and turn the coolant pump on and off. This blue component is a three-phase snubber that filters out any transient voltage spikes generated by the motor. So as you can see, this machine isn't that complicated. It's just a bunch of components that work together to form a control system. Also, I cannot stress this enough. Make it a habit to take pictures. You are now under legal obligation to be the paparazzi for this machine. In all seriousness, documenting everything, especially the original plugs, connections, layouts, and even labels on the machine, is to your benefit and usually does come in handy later. The easiest thing to take off first was the computer. This was straightforward. I disconnected all the plugs and pulled it out. Disconnecting the interface, though, was going to be a bit more involved, so I unscrewed the back cover first to take a look. There were quite a few cables that needed to be disconnected and fished through the opening that led back into the cabinet, but I managed to get it done. Once the cables were out of the way, I unscrewed the last bolt, and just like that, the interface was off the machine. I also unscrewed the metal riser from the cabinet because that wasn't needed anymore. When I was opening up the boxes, I was really happy and pleased with how everything was shipped and packed. The console that I took out is touchscreen and much lighter than the old Dynapath interface. To mount this console, I needed to first attach this arm bracket to the mill. Centroid's documentation shows that for a typical console install, you can mount it at the eye-bolt location. Yet the eye-bolt on this mill was far too big to pass through the bracket, so I had to widen the opening on the bracket a little bit, and after that it fit no problem. I mounted the arm to get a better idea of where the console was going to sit, and I saw the first problem. It was too long. You see, I wasn't really sure how much length I was going to actually need. It could be more or less depending on how the console would be mounted or needed to be mounted. So I thought it would be better to just buy the longest length, since the longest length is the same price as the shortest anyway, and just cut the tube as short as I needed it. So that's what I did. I cut the 5-foot long tube down to 2 feet and welded it back together. I sprayed some black paint on, and the arm looked a lot better now. I prepared the back of the console with the provided adapters and managed to mount the console on the arm. I added the keyboard and tray and was really pleased with the result. I was debating if I should lower the arm or console a little bit, but I realized the whole mill was sitting on wood at the moment, so everything will drop once it gets installed in a permanent location. Going back to the cabinet now, we still have things to remove, like the floppy drive. I needed to mount a transformer in this location. The purpose of this transformer is so it can take the 120 volts AC from the main transformer and step it down further before being rectified. That rectified voltage will be feeding the motors, so it is critical that the motors are not being fed something they cannot handle. Before I bought the all-in-one DC board, I did some research and emailed Centroid to verify that the voltages are safe for the board and the motor. What I found initially is the Servo amplifiers, which are the model GA370 from Glentech, were receiving 182 volts DC. This is a problem for the all-in-one DC board because it's only rated for 180 volts DC max. Looking at the datasheet for the servo motors themselves, which are the MTE 4090 BLBCE from Baldor, they could only handle 150 volts DC. So what was happening here is the servo amplifier was taking the input of 182 volts and converting it to around 100 volts for the output to the servo. The all-in-one DC is not capable of doing this, and so that's the whole reason why we need an additional transformer to step down the voltage and to have a healthy safety margin. Since the all-in-one DC has built-in motor amplifiers, I can remove the old Glentech ones. However, I'm leaving the rectifier and capacitor that's part of the DC bus line so I can reuse it. Once those boards were removed, I started taking a look at the all-in-one DC board. There were additional items like a Windows 10 disk, a wiring schematic, a DC power supply, an MPG wheel, and miscellaneous connectors and cables for the board. Note that depending on what you buy, you might not receive all of these things. It's worth reading Centroid's install manual to get familiar with everything. They have extensive documentation available, and if you take your time to search through it, it will usually answer most of your questions. There's plenty of space where the original Dynapath computer was, and I took my time to install the two power supplies first, and then the main board on top. One power supply was dedicated for powering the all-in-one DC board, and the second power supply was strictly for powering the relays. You generally want to separate the noisy inductive components like relays and servo brakes from sensitive electronics. I wanted to finish running the wires from the interface into the cabinet so you can see how I snake the wires into the tube and push them through. Take your time when you do this and leave some slack on the corners and pivot points to prevent any cable damage. I didn't really record myself taking apart the screen, but you will have to in order to stuff all those cables into this metal box neatly. I did this alone and I felt like I needed 4 arms to hold everything. It's probably best to ask someone to hold the screen for you while you connect everything. There's some connectors on the bottom of the interface for the MPG wheel and an Ethernet cable. We're not using that Ethernet connection in this case because we already have one connecting to the computer internally. I closed up the interface and put the cable covers on. Off camera, I made this metal plate that connected the bundle of cables and the probe connector to the cabinet body. Now it was just a matter of neatly running all the cables down to the board in preparation for connecting everything together. I'm glad I had excellent electrical drawings for this machine's previous configuration. I was able to quickly figure out the appropriate connections to get the relays and contactors to trigger the spindle. You can see here I'm holding these low voltage wires in my hand and making the connection manually to get the spindle started. I made the appropriate connections on the board's built-in relays to give the board control over the spindle. I needed to connect 3 more things: the limit switches, encoders, and the motors, in that order. The limit switches surprised me at first because I thought it was just one switch, but turns out it's one assembly that holds 3 switches. Then there are tabs for each switch that you can adjust. To figure out which wire went to which switch, I did a simple continuity test with my multimeter, and when I manually triggered the right switch, I would hear my multimeter beep. The encoders were a little tricky because I had to deal with a lot of wires. I cut the existing connectors off and used my soldering iron to attach those encoder wires to new connectors. I used both Centroid's schematic and the machine's electrical drawings in order to guide me. For the very first motion test, I decided to not finalize the encoder connector in case there was a problem with how the wires were soldered. Now let's talk about the motors a little bit. When you receive the all-in-one DC board, you'll notice that it has a sticker that tells you to check the resistance of your servo motors before you connect them to power. Centroid has a document that explains the checks you can perform to the motor, but in short, every brushed DC servo motor has a certain expected resistance at its power leads. Over time, the resistance will drop as the brushes wear out inside the motor, coating everything with conductive dust. If you connect a completely shorted motor to the board, you risk damaging or destroying the motor drives present on the motor. These 40-inch-pound servos were supposed to be around 1 ohm, but when I checked the resistance, I was reading between 0.5 to 0.8 ohms, which was concerning. So when connecting up the motors to the board, I decided that adding a half-ohm resistor in series would at least bump that total resistance back up to a normal level. I wired it this way for the first test, and this is how it looked when I was finalizing the wiring with much beefier 100-watt resistors. Now, this is absolutely not how you should wire this, but given the situation and knowing that the servos weren't going to be replaced anytime soon, I thought this would at least give the board a fighting chance of surviving in case a servo decided to completely short itself out during use. I'm very curious what someone from Centroid would say about this, because of course using old servos is not ideal, but if you had to, would a resistor like this even save the board? Before I applied any power to the servo for the initial test, I wanted to disconnect it mechanically from the ball screw. Centroid recommends doing this as well, but I know from personal experience if your encoder is faulty or even if your settings in the software are not configured correctly, you could have a situation where the servo runs away or spins indefinitely, which could ruin your machine and your day. So I removed the belt and the servo was allowed to freely spin without any problems. Once powered on, the board won't energize the servos while any errors or faults are present, but you will be able to see the encoder counts if your wiring is correct, which is exactly what I saw. Turning the servo shaft with my hands made the controller think the X-axis was moving. So the encoder works, but can the motor move? To answer that question, I needed to override all faults and cycle the E-stop. So I hit Alt-I on the keyboard to bring up the diagnostic screen. In here, you can see the status of all the inputs and outputs on the board. And by pressing Control-Alt-I for any input and Control-Alt-F for any output, you can invert any input or force any output you would like. Please do be careful and only do this to inputs or outputs if you know exactly what you are doing and while following Centroid's manuals. Once I cleared all faults this way and reset the E-stop, I was able to type in some G-code that homed the X-axis to move the servo. You can see that the servo will continue to move until it has found the limit switch, but because it's not moving the actual bed of the mill, it will never find it. This was also a good opportunity to test the limit switches that I connected to check if they were working properly. I triggered the switch with my screwdriver, and you can see that the servo stops. Everything seems to be working correctly. Knowing that my wiring was good for one axis, I simply copied that over to the remaining axes. Of course, there's a lot more to this than meets the eye. I spent a few days just working in the software configuring all the settings, calibrating each axis, calibrating the servos, measuring the accuracy and any backlash of the machine, and more. Centroid has all the details on how to properly set up your machine step by step. Even if you do not own any Centroid products, just taking a look at their freely available manuals is a very good way to learn about how to calibrate and set up CNC machines. So when it's all said and done, you power up the machine and the console boots up to greet you with a message to home the machine. You wait until the machine finishes its homing cycle, and then you can start jogging to set up whatever operation you want to run. So far, I managed to design a quick part in Fusion 360 and had the machine successfully cut it out. There's much more I could have talked about in this video, but I think this is already long enough. I had a lot of fun doing this retrofit, and as always, I hope you learned something. If you would like to support me or even talk with me about machines, you could become a Patreon member. Special thanks to my current Patreons. Managing a regular job and YouTube is very tricky, and making consistent content even more so. Patreons allow me to spend more time focusing on YouTube, so thank you.